So now that we've got that reviewed, we're now ready to actually start talking about the trends. This was the note that we did yesterday. There's the example of the orbit number. Further away is a weaker force. And there's the example of the increase in protons. Now let's talk about the trends themselves. The first trend we want to look at is atomic radius. What happens to atoms when we move down the periodic table? And what happens to the size of atoms as we move right across the periodic table? And the size of an atom is determined by the outer shell of the electrons. Where's that valence shell? Because if you were to have two atoms bump into each other, they would only be able to get us so close as those valence shells bump into each other. You can imagine them like bubbles that don't stick together and become one bubble. You know that sometimes bubbles can stick together and become one bubble. Not those bubbles. Bubbles that don't stick together. So if they came along, they'd go and push away. For atoms, the electrons in those valence shells would literally repel each other. Oh, repulsion, get away. All right? So the size of an atom is dependent on where the outer shell is. So really we're asking, how far out is that outer shell? Which is larger, boron or oxygen? When we move to the right across the periodic table, the number of protons is going to increase with the same number of orbits. This results in a stronger electrostatic force on the valence electrons. Which of my atoms has the strongest electrostatic force on its outer electrons? Boron or oxygen? Yep, oxygen, right? Because it's got more. What do you think that stronger pull on the electrons is going to do to the size of the orbit? And now we just need logic. Yep, it's going to make it smaller. It's going to pull that orbit in. As you move right across the periodic table, the number of protons increases. This increases the electrostatic force on the valence electrons. Therefore, oxygen is smaller, right? I guess in here, because there's a greater force, we could say in this little spot, the electrons are pulled in closer. That's it, right? The electrons are pulled in closer, therefore oxygen is smaller. So maybe in here we should have said the electrons are pulled in closer, therefore oxygen is smaller. And if oxygen is smaller, therefore boron is larger, if the actual question is which is larger, right? This is a general statement for the change in the radius as you move across the period in a periodic table. So let's move on. So which one of these is larger? Strontium or magnesium? Yep. Strontium. Strontium is large. Strontium has more orbits than magnesium. The distance to the valence electrons increases, and I'm totally scribbling and out of room. Creases, and that, my smartboard isn't even lined up anymore. And you know what? We really don't need to talk about electrostatic force here. You've got your argument. It has more orbit, and the distance to the outer electrons increases. Therefore, strontium is indeed larger. You make your argument and you finish it off with that concluding statement. That's an easy one. Okay? Questions, concerns? Very logical. Down a group. Again, let's make a general statement. And again, like I said, you're writing the same thing over and over again. It's going to drive you crazy. But I want to get that into your head the way it works. When you're moving down, you're thinking about more orbits. When you're moving across, you're thinking about more protons. So, cations. Again, I want you to be logical. Answering these questions is quite easy as long as we use some logic. What had to happen to our magnesium to make it become magnesium plus 2? What did it do? William? It had to lose 2 electrons. But not only did it just lose 2 electrons, in the process of losing 2 electrons, what else happened? Yep. It lost the outer orbit. And so, which is larger? A magnesium atom or a magnesium plus 2 ion? Yep. The magnesium atom. And then you simply support it with some logic. In this case, the logic's very easily. The magnesium ion lost 2 electrons and therefore lost its outer shell. All right? So, which is larger? The magnesium atom is larger. Magnesium plus 2 lost 2 electrons, and the valence shell. All right? Therefore, Mg plus 2 is smaller. Okay? That's a very logical situation. I don't know if I've got a box coming up here or not, but I will write it in if I don't. I've got a summary on this very simply. Nope, I'm going to write it on the screen. Nope. All cations are smaller than the neutral atom. So cations are always smaller than the neutral atom. All right? Okay, let's take a look at the anions. Which is larger, fluorine or fluoride? Now, let's think this through. Fluorine. How many electrons around it? 7. 1, 2, 3, 4, 5, 6, 7. How many orbits in a fluorine? 2. Fluoride. How many electrons around it? 8. 1, 2, 3, 4, 5, 6, 7, 8. We'll put a square brackets minus charge. How many orbits around that? 2. So the orbit number is the same. So I cannot use this argument here because it hasn't gained or lost any orbits, right? So I cannot use this. Same orbits, same number of orbits. How many protons are in the nucleus of a fluorine atom? What is it? 9? 9 protons. 9 protons. How many protons are in the nucleus of a fluoride atom? Yep, 9. 9 protons. 9. Same number of protons. I cannot use argument number 2. This is the only thing of all of these trends that I'm going to teach you over the next 2 days that we cannot use either of these arguments. We still need to use our logic, but we cannot use that logic. F minus is larger. There is an increased repulsion due to the extra electron in the valence shell. This makes, therefore, the valence shell is larger. Okay? All right?